Well, it is about time, so I guess I'll go ahead and get started. The last time I held class, I went over the atomic theory of matter. I even read a quote from Richard Feynman, Nobel laureate, and sort of an interesting character that has written several autobiographies about his life in physics and his life after physics and stuff like that. Just a fun, brilliant guy. But anyways, I did do that, and I tried to use that as a chance to explain to you how important the atomic theory of matter is and how many things you can do from it. For instance, we discovered that temperature is in fact the modern day definition of temperature is in fact based on the idea that the average random kinetic energy of the molecules or atoms making up an object is in fact directly related to the temperatures. Like literally, you just have to multiply that average kinetic energy by a number, and out pops your temperature, the temperature of that thing in Kelvin. So that's pretty interesting, and we're going to derive that next chapter. But that's one of the things we came up with. Another thing we came up with is as the temperature increases, we'd expect matter to actually increase in length, and if the temperature decreases, we expect matter to decrease in length. And that's mainly because of the vibrations of the individual atoms or molecules, if we're talking about compounds or mixtures. But the atoms actually are vibrating, and they're vibrating quite fast, which means if they're vibrating quite fast, then they're going to go through that equilibrium point and go really far before they come to a stop and then go back. And the fact that they're going really far means that two adjacent atoms could actually, or molecules, could actually interact with each other in such a way that it's not necessarily stable. So, in fact, what happens as the temperature goes up, the average spacing between the atoms goes up as well. So that's sort of the atomic theory of matter's explanation of why things expand and contract with changing temperatures. There's also an idea that, for instance, the reason we smell, for instance, bread baking is, and this was actually the idea of the ancient Greeks. So this was a couple hundred years BCE. Democritus suggested that the smelling of bread was due to these little atoms, which in Greek means indivisible, but it's these little atoms breaking off from the bed and then sort of floating through the air, just like pollen does, and ultimately entering your nose. So that's literally how we smell stuff is these breaking off of atoms. So it's pretty interesting by that. And one of the other things I was able to mention was we talked about this atomic unified atomic mass unit used. It's the lowercase u that we use, and it's a very small unit, so it's really convenient when you're working with things like protons and neutrons. It's actually still quite a bit too big for dealing with electrons, but at least with protons and neutrons, it's right in the ballpark. So we're going to make use of that as in the very first example to solve a problem that's pretty common. And also, don't feel bad if me showing you how to do this makes you think, well, I would have never thought of that. That's perfectly fine. You might would have if you'd given yourself enough time. But the big thing is now that you know, or now that I've shown you how to do it, then you should be able to. So let's go ahead and get started with this example. Are you ready for that?
Ready.
Okay. And feel free, like I said, you can just interrupt me if you have a question. You're not, just for the record, you're not required to be here because this is what we call an asynchronous class, but you are definitely welcomed here. And I would prefer students show up as much as they can so that I can interact with them and give them help as needed. So, anyways, I'm going to go ahead and share my iPad screen with you, and it should be coming up in a second, maybe. Just takes a little while sometimes. Okay, sometimes it's going to take a really long while. See here, see what's doing now. Man, it's going slow. I've never had it go this slowly. Hmm. Let me try starting over again. It's not behaving properly. Let's see. Advanced, iPad, share. Now let's see if I can. Hopefully it'll work now, or at least real soon. Yeah, finally. Okay. So it says the density of aluminum is 2.70 times 10 to the third kilograms per cubic meter, and each aluminum atom weighs 27 U. That's that unit I was just telling you about, the unified atomic mass unit. We're supposed to, or we asked to estimate the average spacing of its atoms using this information. So, what I'm going to tell you for starters is if you look on the periodic table, you will find that the atomic mass of aluminum is about 27.0. Okay, so, and that, in case you've forgotten, that means 27.0 grams per mole. So, let me write that down here. The molecular mass, in this case, it's the atomic mass of aluminum, is 20. Oh, I put this 7 first. 27.0 grams per mole. So that is a really good unit to realize is on the periodic table's masses that you see directly under the HE or the H or the AL or whatever. But notice that it's numerically exactly the same as the mass of the atom in atomic mass units. That's sort of the big deal. In fact, what I mentioned last time was that 1U is in fact equal to 1 over Avogadro's number. But you have to put it in, you have to convert it to grams, to kilograms after the fact, if our kilograms are grams. But basically, it's 1.6605 times 10 to the negative 23. And in this case, it just comes out as grams. So if you wanted to make it in kilograms, it'd be 1.6605 times 10 to the negative 27 kilograms. And actually, that top one was supposed to be 4, not 3. I think I was messing with Avogadro's number and used the 23 instead of the 24. So that those are actually the results. So we're now going to make use of that. The idea that I have in terms of solving this is I'm going to take the density, which tells me that each cubic meter of aluminum has a mass of 2.70 times 10 to the third kilograms. That's literally on the order of tons. Okay, so that's one big thing to notice. But the fact that it's kilograms per cubic meter means I can model this as if it's literally a cube 1 meter on each side. So I'm going to draw that. Let's say we have a cube of aluminum that has a size of 1 meter on each edge, which obviously if it's a cube, all of them should match anyways, but that's what I'm saying here. So this dimension is 1 meter, this dimension is 1 meter, and this dimension is 1 meter. Now, in addition to that, I'm going to imagine that it's made up of atoms. So you've got an atom here, uh, in this corner, and then another atom next to it, and another atom next to it, and another atom next to it, so on and so forth, just like that. Looks like I got another student coming in. So there's a mess load of atoms there. In fact, we also have a mess load of, darn it, I hate it when the thing automatically converts to an eraser. We also have a mess load of atoms going up this side. So we have some more there. And then finally, we also have a mess load of atoms going this way. Okay. Now, in principle, there's no reason to assume that the number of atoms going left to right is the same as the number of atoms going top to bottom is the same as the number of atoms going in and out on this diagram. But if those were three numbers like N1, N2, and N3 are in left, in up, and in back, then the product of them would still equal the total number of atoms in this cube. And what I'm going to do is just go on the assumption that it is the same number, n times n times n, because in some sense, doing that gives you sort of the average anyways. So I'm going to assume that this is a block of n cubed aluminum atoms that has a mass of 2.70 times 10 to the third kilograms. And remember, we decided that because we're using a 1 cubic meter block, according to the density, 2.70 times 10 to the third kilograms is occurring for every 1 cubic meter. So that's why we know the mass of it. Okay. Now, the other thing we're going to do is we're trying to figure out the distance between the atoms. So I'm going to take as a model, just let's just imagine maybe 5 atoms. And I want you to think about just one of those edges, the one going up and down, or the one going left and right, or the one going in and out of the screen. Doesn't really matter, but I'm going to model that as if it's 5. So there'll be 1, 2, 3, 4, 5 atoms. So if n equaled 5, what you would see is that this distance right here would be called d, and then this one would also be called d, and this one would be also called d. And in principle, they should all be sort of the same, but the main thing is because the process we're doing with it, we are actually sort of getting an average anyways. But the main thing I wanted to show you here is that by this model of imagining 5 atoms in a row, we can take a poke at how long that row of atoms is. Let's call that length L, okay? And ooh, I drew it a little long on that end there. Let's draw that length L. And from this model, we can say L is equal to 4 times d. Would you agree with that? Because remember these the lines that I drew vertically to make the measurement, they're actually going to the dead center of the atom, and then to the dead center of the next atom, and to the dead center of the next atom. So there's no gaps in between the line for a D on the right versus the line for a D on the left. So I think you can see that L would be 4 times D. Does that make sense to you guys? Okay. So the other big thing to notice is that if it was 6 instead of 5, then we'd have 5 spaces. So in general, this model is more explicitly covered by n minus 1, oops, n minus 1 times d is equal to L. Okay. Now in our case, the L is equal to 1 meter. 1 meter, and n is a huge number. So 1 meter is equal to n minus 1 times d, so that d would equal 1.00 meter divided by n minus 1. But since n is a huge number, d is very precisely approximately equal to 1 meter divided by n. So if we've got a way to find n, then we will have a way to determine what the spacing is for the atoms. Or molecules, if we were doing molecules and imagine them being in a cubic lattice like this. So does that make sense? Feel free to ask me any questions if you don't understand. Okay. So right now I've got a geometric description of a block. I have a atomic description of the block that suggests it has n cubed atoms in it, and I have a mass description of the block. So if I could somehow convert that mass to a number of atoms, then I would know n cubed. So the way that chemists because chemists know that they have to work with integers, multiples of atoms. In other words, you can't have a half an atom, you can't have a tenth of an atom, you can't have seven eighths of an atom. So chemists have to work with whole atoms when they're thinking about reactions, and hence they come up with the idea of the mole of a substance, MOLE. The mole of a substance is basic, or the mole of anything is basically Avogadro's number of things. So you could have, for instance, a mole of playing cards, and you would have 6.022 times 10 to the 23rd playing cards. Or you could have a mole of fried chicken, in which case you'd have 6.022 times 10 to the 23rd fried chicken pieces. Okay, so that's what we're going to do is we're going to take that mass that we have, which is 2.70 times 10 to the third kilograms, and we're going to use the atomic mass of aluminum to figure out how many atoms there are. So let's go about that. So now, I don't want to write that. Let's see. Now we'll use the atomic mass of aluminum to determine the number of moles of aluminum in the block. Now, the conversion from mass to number of moles is done like this in case you've never had chemistry or in case you've even forgot it. And it's usually indicated by a lowercase n like we did here. And what you do is you take the mass of the aluminum and divide it by the molecular mass of aluminum. Okay, notice I used a capital M for molecular weight, or in this case, atomic weight. Now, the other problem is I showed you the periodic table when it says 27.0 under aluminum, it actually says 26.98, if I remember correctly. I think it's 26.985, something like that. If you round that to one decimal place, it comes up to 27.0. That's why I wrote 27.0. But the main thing is the 27.0 that you'd see right under the aluminum on a periodic table is understood to have units of grams per mole. It's also understood that it could have units of just the atomic mass unit U per atom. So that's another way of doing it. In this case, obviously, we're interested in the grams per mole, but since it's grams per mole, we know that we have to have the mass not in grams, but in kilograms. I mean, not in kilograms, but in grams. So we already had the mass was 2.70 times 10 to the third. If I want to make that into grams, then I'm going to write 2.70 times 10 to the 6 grams, because remember, I'd have to multiply the kilograms by 1,000 to get the number of grams. So I'm going to take that 2.70 grams of aluminum and I'm going to divide that by 27.0 grams per mole. Okay. And what that's going to give us is, luckily, these two, the density and the atomic mass, both have the same first two significant figures, our first three significant figures. So it's going to come out to a nice, easy number. We'll take 2.7 times 10 to the 6 divided by 2.7, or excuse me, divided by 27. And that gives me 1 times 10 to the 5th. And that's moles of aluminum. Okay. Now remember, I said moles of aluminum. It means the number of Avogadro's numbers of atoms. So a single mole is Avogadro's number. Therefore, 100,000 moles like this is 100,000 times Avogadro's number. So now I can say that N, which equals the total number of atoms. Of course, if we were using molecular weight, that'd be the total number of molecules. But the main thing is the total number of atoms or molecules would be the number of moles, lowercase n, times Avogadro's number, n sub a. So now I can say that in the total number here, and actually it's really unfortunate that I used the n uh, for the for the number of atoms along the side because I'm using the same n here. It probably would have been smarter for me to use something else. In fact, let me do that. Let me say instead of n cubed, let's say let's call it a cubed just to make it a little less messed up. So I'm going to say this is a, and it has a cubed atoms, and I'm going to say this model that we did was using a as the model. So I'm going to also change this to a here, just so we know exactly what I'm doing in such a way that I don't confuse the two M's. I apologize for that. I've literally worked this for years and didn't once notice this, even though I've been doing it all this time. I would have thought that I'd thought of it before, but I guess not. So, anyways, we're going to get the total number of aluminum atoms by taking this 1.00 times 10 to the fifth, and I'm going to multiply that by Avogadro's number, which is 6.022 times 10 to the 24th. Or excuse me, 10 to the 23rd. So this is going to be 1.00, oops, let's leave that off, times 10 to the fifth moles times 6.022 times 10 to the 23rd atoms per mole. Okay? So now that we have that, all we have to do is complete the multiplication. So I'm going to say this times 6.022 times 10 to the 23rd, and this gives me 6.022 times 10 to the 28th atoms. Now that's the total number inside of the block. Okay, so we now can set that equal to a cubed. So setting a cubed equal to n, we can find a, and therefore d, which is what we're asked to. So I'll say a cubed is equal to 6.022 times 10 to the 28th, like that. And the way we solve such an equation is we take the cube root of both sides, like the always rule, whatever you do to one side of the equation, you must do to the other. So that's all I'm using here. And wow, that was really a bad attempt at writing a 3. So that's a cube root of both sides. And what we're going to get is that A is equal to, I'm going to raise this 6.02 times 10 to the 23rd. I'm going to raise it to the 0.333333, or in other words, the 1/3 power. And that's the same thing as taking the cube root. So this gives me 3.92, actually 3.920 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the ninth atoms. So that's how many atoms there are along one side. We only put in basically 2 sig figs because we start off with that. Actually, we did use 3 sig figs because we started off with that 29 or 27.0. So I'll just underline that last digit, which I'll underline here and underline here as well. And now all we have to do is use our formula, which we derived from our little model. So D is equal to 1.00 meters divided by A. So if I take 1 and divide it by the last answer I computed, then I should get the distance. And lo and behold, that distance is 2.55 times 10 to the negative 10th meters. And that should be the average separation between adjacent atoms of aluminum in aluminum at 20 degrees Celsius. Okay. And I say at 20 degrees Celsius because that happens to be the temperature at which the density of aluminum is 2.70 times 10 to the third kilograms per cubic meter. It doesn't change too terribly much from one temperature to the next, unless you're going huge temperature ranges. But still, it's just important to say that because, as we know from the atomic theory of matter, if the temperature goes up, obviously the spacing is going to go up, and that would make it less dense. So, any questions on that? All right. So there's also a another type of thing we have to consider is we have to deal with temperatures. And the section 17.2 of your textbook is really about temperatures, temperature scales. It's actually called temperature and thermometers. And what I want to explain to you is that a thermometer can be made of any device or anything that you found to have properties that change as a function of temperature. So, for instance, we know uh, from everyday life that when we connect a resistor to a wire and run a current through it, we can do a series of experiments to determine what the resistance is. And what we discover is not only can we get a resistance for a particular resistor, but if we were to change the temperature at which that resistor is carrying that current, we'd find that the resistance changes as well. And not only that, it changes in a very descriptive way or a very definable way. Let's put it that way. Meaning we know an equation that can actually let us figure out what the resistance would be at another temperature. We're going to actually investigate that later on in the semester, but the main thing is to know that temperature and resistance have some kind of correlation that we understand pretty well. So we can use resistance as a property that we could use to make a thermometer. We could also use, for instance, the pressure times the volume of a certain amount of gas. So if you put a certain amount of gas, meaning a collection of a certain number of moles of gas, if you put that in a constant volume cylinder, or constant volume container, then you can make sure you keep the volume the same. And what you can do is have that container reach various temperatures. And when you reach those various temperatures, you can use a gauge on the actual container to figure out the pressure. And the volume, since it's fixed, is something you could measure one time and just have every time. And by doing that, you just multiply P times V and you'd get a very specific answer. Well, it turns out in the ideal gas law that P times V is equal to the number of moles, which is fixed, times the ideal gas constant, which in the physics world is fixed, times the temperature. So that is another way you can have a temperature. It's called a fixed volume gas thermometer. There's a lot of other things as well you can use. You can use, for instance, the expansion of a metal. You can use the expansion of a liquid. That's the more typical thermometer you're probably used to. If you use a thermometer that's got a red liquid in it, that's normally what we call an alcohol thermometer. It uses some form of alcohol. And down at the bottom, there's this little bubble shaped piece of glass where it allows a good volume inside of it, and then a narrow little cylindrical empty tube runs all the way up through the center of that thermometer, and the volume of it is fixed to the volume of that bulb at the bottom plus the volume of that little cylinder going up. So for however high that cylinder is, that means a different volume. So if you increase the temperature, the only way that thermometer can allow its alcohol to change its volume is by going up the little cylindrical tube, which is basically a vacuum above it. So it just moves its way up. So that's the way we make a liquid thermometer. You can also use mercury, which is really convenient because mercury has such a high density. It doesn't take very much pressure, or I should say the other way around. It takes quite a bit of change before you can get a appreciable measure because of how dense the mercury is, and therefore you can measure things to a very small gradation. Anyways, now that we have that in mind, I wanted to show you a couple of examples of stuff that regarding this. So let me stop sharing this screen for a second, and I'm going to go to sharing my a picture from the page of the book. So I'm going to share this picture right here, even though that's not the picture I care about. So this is a page straight from Giancoli's edition. You've probably seen this, or you've at least heard it as you rode over one. If you go across a bridge, there will be inevitably one of these, and as you hit it, you'll hear a clunk, clunk. Clunk, clunk, something like that. Basically, what that is notice the space in between the teeth and the hole for the tooth. That space allows this hunk of concrete on each side to actually expand and contract. So when the temperature gets really hot, it expands and gets longer and longer. So the ends of these little teeth will slowly slip into the hole a little bit further. Now, ideally, what you'd want to do is install this on, say, one of the hottest days there are, and put it where it's still a good distance away. Like if you spaced it this far apart as it's shown right now in the picture, and you did that on a day when it was like 110 degrees, then that would still give you quite a bit of room for it to expand a little bit more in case a record breaking day comes later on. And in so doing, it doesn't allow the forces of nature to actually cause the two slabs of concrete to buckle. But that's literally what they would do if it wasn't for expansion breaks like this. They would push against each other, and the force is so great that it would literally cause the concrete to crack or break or even pop up like that. And you can imagine how horrible that would be for our car to hit a ramp on the middle of a bridge. So, anyways, that's a good thing to show you, even though that wasn't what I was shooting for. Uh, this is a bunch of different thermometers that they had at the Royal Academy. This is one in Italy. But anyways, another thing we can use, and you might have already seen this if you've ever lived in a house with an older thermostat. If you open up the thermostat, you'll see a coil of copper or something like that inside of it, just like this. Now, this, I've normally seen these sort of mounted to the front of a gas grill, for instance, or even a charcoal grill, because what's going on here is we have a bimetallic strip. It's a metallic strip made of two different metals. So you can imagine this green, for instance, is let's say copper, and then let's say the blue on the other side is aluminum or something. And because each material, aluminum, steel, copper, all these different materials, or even compounds, they have certain characteristic properties, and those characteristic properties are a function of the material that you're using. So the fact that they're two different materials means it's highly unlikely, unless you're just unlucky, but it's highly unlikely that the two materials expand at exactly the same rate. And by rate, I'm not meaning like a velocity. I'm meaning like the amount of change in length per change in temperature. So that amount of change in length per change in temperature is almost always different from one substance to another. So when you connect them this way, what's going to happen is the one that has a higher rate of expansion, when you heat it up, it's going to get longer than the other one gets, even though at the same temperature, they actually have the same lengths like it shows on the left. But as you heat it up, this green one, which has a higher coefficient of linear expansion called alpha, that one's going to expand more than the blue one did, and therefore it's going to bend towards the blue one. So that's a way that you can actually do it. And if you look down here, that's what's going on here. They actually have this bimetallic strip mounted, fixed right there, and you then have the material goes around and around and around. It's just a big spiral because it turns out these changes are very small. The coefficient of linear expansion is on the order of 1/1 millionth. So it takes a significant change before you get a significant change. Therefore, the longer the piece of bimetallic strip is, the more it'll move. So what happens with this one is if the temperature goes up, then it's going to bend even more, and that would actually cause this device to, in this case, it's going to move that way towards a higher temperature. And then when the temperature goes down, it's going to move back this way. It looks counterproductive in there, so there might be something fishy with it. In other words, it looks like it would be the other way to me, but it might just be my lack of familiarity with the actual individual coils. I'll show you something else that the coils can do in a second. So before I go on to the temperature scales, now that you've seen that, I'm going to draw you a neat example of how such a uh, bimetallic strip can be used. So let me switch back to sharing my iPad screen, and let's hope it goes faster this time. It appears like it will. Okay. So, and literally based on that photo I just saw, I may be sort of explaining the way this coil rotates backwards, but it doesn't matter. The main thing is whichever way it coils is going to change. So let's start off just showing you what I mean. So if you open up a thermostat in your house, the thermostat's the thing that you adjust to change the air conditioner temperature or the heat temperature, mainly the temperature at which you wish the air conditioner to come on and the temperature at which you wish the heat to come on. So if you were to open one of those and it's not a modern electronic one, what you would see is a bimetallic strip like that one made out of copper, and it'll spiral around and around and around and around and around and around like this. And now what I'm going to show you that I think is kind of neat is they take and put sort of like a Tylenol capsule made of some kind of clear glass. So it's shaped like a Tylenol capsule, but it's just basically a clear glass like pill basically. And it's a clear glass, so it doesn't allow things to leak in and leak out, but it also has little probes of metal poking through the sides, but they're sealed up with the glass. So what happens is you fill this Tylenol capsule up with mercury, and the reason why you use mercury is a liquid, so it can readily flow, but it's also a conductor. So it can become a liquid and it can still flow, but it can also conduct electricity. Because what they do is they take and they jab a piece of wire into the actual cylinder, I mean, into the actual pill, and then that wire is connected to the power source, which you might think of as a light receptacle. Okay, so that's the power that could come in and go directly to your heater or to your air conditioner. Now, in addition to that, they'll have a second wire that comes over here and stabs into the pill again. Only this one runs to a unit that can cool down the house. So this one runs to the air conditioner. Okay. So when it gets hot enough, basically this coil, again, this is the part where I was telling you I might be wrong about the direction it goes, but it doesn't really matter. The main thing is it does this and it's going to go one way or the other. But I'm assuming as T goes up, the bimetallic strip, oops, uh, coils clockwise. Again, this is the part where I'm telling you I might be misanalyzing the direction it go, but it doesn't matter because, like I said, one way is a clockwise rotation, the other way is a counterclockwise rotation. All that would be different from my explanation versus the real one would be you'd put the air conditioner on the other side and the heater on the other side as well. So right now I have my air conditioner on the right. Now, as it gets hotter and hotter, what you saw was the mercury pulls over to the right hand side of that cylinder, that little pill, and therefore that mercury conducts electricity from the light receptacle to the AC and turns the AC on. On the other hand, if it gets cold, oops, let me use a blue for this to, so temperature goes down means it goes this way. What we would do then is we might have the cylinder this way, or actually I shouldn't draw it that far off. It's a little misleading. Well, that's a lot harder to erase than I thought. So again, the main thought is that the metal is going to uncoil, and therefore this pill, this Tylenol capsule full of mercury, is going to have the mercury now look like this. Okay, now that still is connected to the black wire like that. So the power is still stabbing into the mercury. But on this side, there's a wire that stabs into it, and this wire goes to a heater like that. So that's a really brilliant mechanical way of implementing something that would be nice to do electronically or automatically. So they managed to figure out a way to automatically turn an AC on or turn a heater on, and it's through that bimetallic strip. So I think that's really interesting and cool, and it should help you better understand how bimetallic strips and that sort of thing works. So now that we have that, I want to talk to you about the various temperature scales we use. You're probably familiar with what used to be called the centigrade scale. There's still some older people around that call it centigrade, but it's now called the Celsius scale. And you're probably more familiar, if you're from America, you're probably more familiar with the Fahrenheit scale. So those are the two temperatures that we're most familiar with, or two temperature scales we're most familiar with. But there's at least two more. Actually, the website that I'm getting ready to show you a picture from has several more, and there's been a lot of them over time. But really, there's an absolute temperature scale that we use that's just like Celsius, and that temperature scale is called Kelvin. And then there's another absolute temperature scale that's just like Fahrenheit, and that one's called Rankine. And you don't refer to temperatures in the Kelvin scale as degrees Kelvin. You just say Kelvin because the degree, which you might have thought about this before, but have you noticed it's kind of odd that degree is what you use to measure angles, but it also happens to be what you use to measure temperature and stuff like that? That's kind of odd, right? Well, the reason why is we use the degree as an indicator that it's an arbitrary scale. So when we decide, or I say we, when the human species decided to make up a scale for angles, they could have used anything they wanted to. They chose to say 360 degrees, partly because they were using a base 60 number system, and the base 60 number system was really convenient when working with 360 because 360 allows 60 to go into it and powers of 60 and stuff like that. Or if you even think about it without those weird number systems, 360 is just a number that a lot of numbers go into. It's obviously even, so that means two goes into it, but also four goes into it, and also eight goes into it, so on and so forth. But it also allows three to go into it, and six, and stuff like that. So they arbitrarily chose 360 to represent the full number of angles or the full angle through a circle. Because of that, it's an arbitrary scale, so you keep degrees on it. Celsius and Fahrenheit are somewhat arbitrary in that they're both based on water. Specifically, the freezing point of water in the Fahrenheit scale is 32, and the freezing point of water in the Celsius scale is 0. And then the boiling point of water in the Fahrenheit scale is 212, and the the boiling point of water in the Celsius scale is 100. So it's completely based on water, and water is extremely important to humans and most of the animal life that we know on the earth, but it's still somewhat arbitrary in that we could, in principle, meet another alien species from a distant galaxy or at least just a different star system, and they might not be as hinged or as finding water as important. We don't know. I mean, we don't really understand all the nuances of how life could be. We do know what it is within our own biology, but beyond that, we don't know. So it's still somewhat arbitrary. What happens with these scales that I'm talking about now, the Rankine and the Kelvin, is this. If you made a plot of temperature on the vertical axis versus volume on the horizontal axis, what you see is that temperature, as temperature goes up, the volume goes up, or as volume goes up, the temperature goes up, that sort of thing. But if you plotted this, say, for hydrogen gas, then what you get is this line like this. Now, I drew it all the way to here, but in principle, when you get to lower and lower and lower temperatures, there's going to become a point at which the gas that you started with was no longer gas. Now, hydrogen and helium might be different in that respect, but in general, you just know that's going to happen. Now, here's the neat thing. If you also make a graph of, say, helium, well, it does sort of the same thing. There's helium gas. What about water vapor? Well, if you did a water vapor graph, it would do the same thing. And of course, the helium was gas as well. If you do chlorine gas, if you make a plot of chlorine gas, you're going to get something that looks like this. But again, all these lines would stop becoming lines down there where they're about to hit the axis. But the neat thing is, no matter where or what element or compound you use, if you plot a graph of temperature versus volume for that gas, they all converge on this one spot. And that one spot happens to be negative 273, I think, 0.15 degrees Celsius. So, in that sense, in the sense that every substance we've ever found, when we make a temperature versus volume graph for it, they all converge at one point on the temperature axis. And that one point is what we recognize as the absolute zero. And it should be absolute because it literally is for every element and compound. So, that's kind of cool. So, that brings us to the idea that the temperature in degrees Celsius should be equal to the temperature in Kelvin uh, minus 273. And it turns out that there's a similar formula for the temperature in Fahrenheit to be converted to the temperature in Rankine. So you could say, for instance, the temperature in degrees Fahrenheit is equal to the temperature in Rankine minus, in that case, I want to say it's 492. Uh, and I don't know the decimal point on that, but that's sort of what it is. Okay. So that's the case. Now, what I'm going to do for a second is I'm going to, oops, somebody else came. I'm going to stop for a second, stop sharing my screen, and show you a graph of these scales. So let's go ahead and share the scale. I've got another student coming in now. Oh, and by the way, just so I can keep track of who did come, even though I don't, like I said, you're not required to come or anything like that. If you guys would chat me your first and last name, then that would be helpful because I could use that as sort of a role. So do that. I want to remind everybody that this will be put on the internet. So if you're like in hiding or something and don't want your name on the internet, you might want to just use like your first name and the first initial of your last name, like Macy has done here. I can do that for you if you don't know how. But if you don't care, like it doesn't matter if your name's seen on the internet, then don't worry about it. Now, what I'm going to do is I'm going to share the screen that I have right here, only now I have a different screen showing. There you go. So that should do it. So here's those temperature scales that we're talking about. So you can see the Celsius scale, and there's something really critical for you to notice here. The Celsius scale from the freezing point of water to the boiling point of water is 100-degree difference. And that's 100-degree in Celsius, of course. Now, the difference in temperature for Fahrenheit from the freezing point of water to the boiling point of water is from 32 to 212. That's a difference of 180. So that's a big difference. What that means is the size of a Fahrenheit degree is markedly smaller than the size of a Celsius degree because a Fahrenheit degree takes 800, I mean 200, 180 of them to get from freezing to boiling of water, whereas a Celsius one only takes 100 of them to get from freezing to boiling. Okay? Now, that's also important because that points us to a way in which we're going to convert back and forth between Celsius and Fahrenheit. There is a formula you can use, and I won't be able to tell whether you're using that formula or not, but I'll tell you that I've learned from educational research that there is a more pedagogically sound way of teaching you how to convert back and forth between Celsius and Fahrenheit, and that's what I'm going to teach you. But it hinges on the fact that those two numbers of degrees is 100 and 180. And that's a big difference. So I'll be showing you that in a second. But you can see here, both of them have an absolute zero, which corresponds to a very specific temperature, specifically negative 459 Fahrenheit, right? And specifically negative 273.15 Kelvin or Celsius. So that's what the absolute zero is. And you can see 0 Kelvin marked there in the Kelvin scale and 0 Rankine marked there in the Rankine scale. And the fact that they're all the same height tells you it's the fundamentally same quantity. So, anyways, that's a nice little picture to have. I'll probably be stealing it and including it in my notes in the future. So, let's kill that for a second and let's go back to sharing my iPad screen so you can see how we're going to convert. So, this should pop up any minute now. All right. So what I'm going to tell you is I'm going to give you a little poem that I learned to help my uh, Blackwater students. I used to do some contract work for Blackwater, which became Z, which became Academy. Right now, I think they might be known as Academy. I can't remember, but anyways, I had to teach their machinist metrication. In other words, I had to convert them from the British system that America and I think Myanmar, the only two places on the planet that use them. But we were still using them, and they were getting ready to make a some vessels to replace up armored Humvees. I think it was called the Grizzly, and they needed to do all that in the metric system. So I had to teach them metrication, and to teach them the aspects of temperature, I memorized this little poem, and it says 30 is hot, 20 is nice, 10 is cold, 0 is ice. So that should help you keep straight as to what these temperatures are in Celsius compared to everyday life. I think I recall that human body temperature is like 37. Uh, I will admit that this 20 degrees is wonderful for me as a fat person. I just love 20 degrees Celsius. But what we're going to do is I'm going to use what I just told you, specifically the fact that freezing of water and boiling of water. That's going to be 100 degrees Celsius, and this is going to be 0 degrees Celsius, but it's also going to be 212 degrees Fahrenheit and 32 degrees Fahrenheit. Therefore, the difference is 180. And notice how I write this. I write this as Fahrenheit degrees. That's a little trick we use in physics and chemistry to let us know when we write down a number, is this an actual temperature or is this a difference in temperatures? So a difference in temperature should be written Fahrenheit degrees or Celsius degrees, whereas an actual temperature should be written in degrees Fahrenheit or degrees Celsius. So this one, on the other hand, this distance is 100 Celsius degrees. Now, that teaches us a few things. For starters, we can say that 180 Fahrenheit degrees is equivalent to 100 Celsius degrees. So when you learned about how to convert units, you learned that equivalent statements like this, 180 Fahrenheit degrees equals 100 Celsius degrees, means you can make a fraction by putting the 180 on top and the 100 on the bottom, or the other way around, and then that fraction can be used to convert units. Now, when we do this, we can actually make some simplifications. So you can get, for instance, 18 Fahrenheit degrees over 10 Celsius degrees. You could also write this as 9 Fahrenheit degrees over 5 Celsius degrees, or you could even write it as 1.8 Fahrenheit degrees for every 1 Celsius degree. Now, you also have the other part of the fraction, which of course would be 100 Celsius degrees per 180 Fahrenheit degrees. And that one's still the same thing. It just becomes, of course, 10 over 18 instead of 18 over 10. So 10 Celsius degrees over 18 Fahrenheit degrees are 9 or 5 Celsius degrees over 9 Fahrenheit degrees, that kind of thing. But we can use that. So what I'm going to do is I'm going to show you the method that I recommend based on sound education research of converting back and forth between Celsius and Fahrenheit. So here's my example. What is 30 degrees Celsius in degrees Fahrenheit? So that's the example I'm going to solve, and this is the solution. And the way I do it takes a few steps, and these steps are the same, though the wording's a little different whether you're going from Celsius to Fahrenheit or Fahrenheit to Celsius. So the first question I ask myself is, one, how far is 30 degrees Celsius from freezing? And what I mean by that is, how far is that from the temperature at which water freezes? And specifically, I mean within the Celsius system. Okay, so what we have to do here is we do 30, oops, we do 30 degrees Celsius minus 0 degrees Celsius is equal to 30 Celsius degrees. So the answer is 30 Celsius degrees. Now you see we've already converted it to Celsius degrees. Now part two, we're going to say, actually, let me write it a little bit further to the left. We're going to say 2, how far is this in the Fahrenheit scale? Oops. Okay, so in other words, we're now going to use our conversion factor. I'm going to write 30 Celsius degrees, and since I'm converting units, I'm going to write that over 1 because my students aren't necessarily always that strong in fractions, especially post-pandemic. So I need to multiply it by the version that has the C in the bottom. So I'm going to divide it by, or multiply it by 18 Fahrenheit degrees per 10 Celsius degrees. And that's easy peasy because I know that 30 divided by 10 is 3, and then 3 times 18 is 30 plus 24 is 54. So that's 54, in this case, Fahrenheit degrees. And remember, the 30 degrees Celsius was technically 30 degrees above freezing, and this now says 54 degrees Fahrenheit or Fahrenheit degrees above freezing. Okay. Now I did use freezing. If I was using a temperature like 112 and I want to convert that from Celsius degree from degree Celsius, then I would have instead of using freezing, I would have used the boiling point. That's perfectly fine. You can use any points you want, but the two that we have that I've shown here are just the freezing point and boiling point of water at 1 atmosphere. So now that I have how far it is from freezing, now all I have to do is convert it to the actual temperature within the Fahrenheit system. So 3, what is that temperature in degrees Fahrenheit? So again, I'm making use, even though I didn't write it down, I'm making use of the fact that I know I was above freezing. So I'm going to go 54 Fahrenheit degrees above freezing in the Fahrenheit scale. So that means I'm going to take 54 Fahrenheit degrees and add to it 32 degrees Fahrenheit. Notice how these units look different and I can add them. That's because this was just a trick we did to keep our wits about us in using the Fahrenheit degrees. You still can use them mathematically. So when I add these two together, I think you can see that we get 86 degrees Fahrenheit, and that is the actual temperature of 30 degrees Celsius. So yeah, that's not a comfortable temperature, especially for a fat dude like me. That makes me, want to punch a baby or something. So, and just playing, of course, I don't want to punch anybody, but definitely not babies. I love babies. So, anyways, any questions on that? Yeah, I'm a goober. All right, let me show you the same thing, but this time I'm going to go from Fahrenheit to Celsius. Okay, so here's another example. What is Well, let's do the 98.6 one. Since I can never remember what it is. I think it's like 35 or 37, but yesterday I thought it was 32, so who knows? What is 90? Oop, no, I don't want that because I want to go from Fahrenheit to Celsius, not from Celsius to Fahrenheit. So I can't use that. Let's do 35. So what is 30? No, I can't do that. What is Now I did do Celsius the first time, yes. So we'll say what is, yeah, 98.6 degrees Fahrenheit in degrees Celsius. So that's the problem we're going to solve. Yeah, that's cool. And here's our solution. We still have our same facts that we want to make use of, but I'm going to start with number one, uh, and that is how far is this temp from freezing? And what I mean by that again is within its own scale. So it's the same question I'm asking both times, but because I'm using it this way and not being extremely specific, it's automatically just understood to be the same scale. We will notice, by the way, that actually this is a really good time. No, it's not. No, that's good. I was going to say this is a good time to use 100, but not for 98.6 Fahrenheit. For 98.6 Celsius, it'd be a good time. So what I'm going to do is I'm going to take 98.6 degrees Fahrenheit, and I'm going to subtract it from 32.0 degrees Fahrenheit, and that's going to give me, obviously I should be able to do the math, that should be 66.6. Ooh. The devil's number. 98.6 minus 32 is 66.6. Yep, I was right. 66.6. And notice since I've done subtraction, I'm going to call this Fahrenheit degrees. Now, two, how far is this in Celsius degrees? And I'll say, by the way, I'll remind myself that this is 66.6 Fahrenheit degrees above freezing. Okay, because we need to make sure we know that because later we got to either add to the freezing temperature or subtract from the freezing temperature. So how far is it in Celsius? Well, in this case, we just use our fractions. I've got 66.6 Fahrenheit degrees. I'm going to write that over 1 for the same reason because we're getting ready to use fractions. I've got to have my Fahrenheits down in the bottom. And of course, you recall when we had the Fahrenheits in the bottom, you could have the 9 in the bottom and the 5 in the top. So I'll do that one. And now I'll take 66.6 and I'm going to divide it by 5. That gives me 13.32. And now I'm going to multiply, or excuse me, I was supposed to divide it by 9. Let me redo that. 66.6 divided by 9. That gives me 7.4. And then 7.4 times 5 should be, what, 35.8? Oh, it said 37 flat. Oh, yeah. Okay. 5 times 7 is 35. 5 times zero point 0.4 should be 2. That's right. Okay. So this gives me 37.0 Celsius degrees. Of course, making note that the Fahrenheit degrees canceled out. So now I have the difference between this temperature and freezing. And we know, of course, that it is above freezing. So now I say part 3 is what is this temperature in degrees Celsius. Okay, so now all I have to do is take that 37 degrees Celsius and add it to the 0 degrees Celsius, and that'll give me the Celsius degrees. So 37.0 Celsius degrees plus zero point 0.0 degrees Celsius is 37.0 degrees Celsius, and that's our answer. So it does turn out that 98.6 degrees is 37 in Celsius. Any questions on that one? Now, I'm not requiring you to convert between Rankine and Fahrenheit, but I will require you to convert between Celsius and Fahrenheit, or Celsius and Fahrenheit, or Fahrenheit and Celsius, as well as between Celsius and Kelvin. Specifically because we're covering the ideal gas law, and the ideal gas law requires you to use the temperature in Kelvin. You cannot use anything but Kelvin in the ideal gas law. So, anybody have any questions on that one? All right, so that's sort of my description of the thermometers and temperature and stuff like that. If we go into section 17.3, that's called thermal equilibrium and the zeroth law of thermodynamics. That might seem a little odd to you, but basically, if you're familiar with math and geometry specifically, you'll know there was some really sort of weird principles like the reflexive principle and stuff like that. Because of that, we later looked at science with the same sort of eye that we look at mathematics and realized we probably should have mentioned this. So, what the zeroth law of thermodynamics is this. Let's imagine, for instance, that this right here is in thermal equilibrium with the liquid in this TCC cup. Okay. And what I mean by thermal equilibrium is that they're basically the same temperatures. We'll discuss that in a second. But the red pin here, which is, you can sort of picture it like a thermometer, is inside this cup of liquid, and they're all at equilibrium, and the thermometer is reading, 70 degrees Fahrenheit, say, right? Now, if I take this object, which was in equilibrium with the blue cup, and then put it over here in the silver cup, and I discover that it's also in thermal equilibrium with the silver cup, okay, then the zeroth law of thermodynamics says that the silver cup and the blue cup are also in thermal equilibrium. It seems like you really didn't have to say it, but in some sense you did. So that's what the zeroth law of thermodynamics is. Any questions on that one? I will reiterate what I told my students in class, and this bit me in the hiney one time when I was in grad school. It turns out it should be obvious. It's obvious to me now in retrospect. But my very first test in my very first class in grad school, at least at Chapel Hill, not at East Carolina, the professor gave us a really easy chucker question. Only I didn't get it because I didn't think of it, which was kind of stupid. Okay. But here's the deal. If you see a whole chapter called, let's say, uh, First Law of Thermodynamics, you probably should read the First Law of Thermodynamics and commit it to memory. Okay. Uh, Alternatively, if you see something called a law and you use it over and over again and you're taught about it and there's even subsections of a chapter named after it, you should probably commit that to memory. So just like in the 241 course, you probably did commit the first law of Newton's first law of motion to memory. Hopefully, you definitely committed Newton's second law of motion to memory and Newton's third law of motion. You probably did have that memorized just because it was, straightforward to say an object or for every action there's equal but opposite reaction. But the key point is do that. What happened to me was we had covered nothing but Maxwell's equations for, like 2 weeks. And his first question was state Maxwell's equations and the boundary conditions. And stupid me, I knew the equations, but I couldn't remember the boundary conditions. So I lost a good 10 out of 20 points, which was, horrible. So I just want y'all to prosper where I screwed up. All right. So in other words, when I just read the zeroth law of thermodynamics to you, you might want to commit that to memory. Okay. Now, let me talk about thermal equilibrium. So, if you put two objects in contact with each other, if they're not in thermal equilibrium, heat will flow from one to the other. Okay. What matters or what makes them in thermal equilibrium is that they have the same temperature. Okay, just the same temperature. And remember, the modern definition of temperature is that basically the temperature is a measure of the random kinetic energy that the molecules or atoms in the object has. Okay. Because of that, you can imagine what if Mr. Younger, puts this rock, this cool baby Yoda rock that some unknown person left in my mailbox for me. Actually, I think it was a kid down the street that was really sweet and just kind to people. But anyways, and I say kid, she's probably a grown woman now. But anyways, if we put this in contact, this Yoda rock in contact with this eraser or with this marker, then if they're in thermal equilibrium, that means they both have the same temperature, and that means the molecules or atoms in this pin and the molecules or atoms in this rock both have the same average kinetic energy. So when they collide, which at the microscopic level, essentially a lot of collisions are really what we call elastic, therefore kinetic energy is conserved. So because of that, when one atom or molecule that has a certain kinetic energy runs into another atom or molecule that has the same kinetic energy, then they leave without altering each other's kinetic energy. And that's exactly what happens, for instance, when an atom or molecule bounces off a wall, an immovable object, for instance, is it basically doesn't lose or gain any kinetic energy. So whenever two objects have the same temperature, the atoms bump into each other and don't distribute any energy across the barrier between them. However, if let's say Baby Yoda atoms had a higher kinetic energy, then when they hit the other atoms or molecules, they would cause those other atom or molecules to speed up, and the atoms or molecules in Yoda rock would actually slow down. And over time, that one atom being slower would eventually cause all the other atoms to reach a new average kinetic energy, and that new average kinetic energy would be lower than the kinetic energy they had. Similarly, eventually all the atoms in the pin, which were in fact a higher kinetic energy, they're eventually going to all reach an equilibrium that is at a new higher equilibrium, and therefore the colder object got a higher temperature and the hotter object got a lower temperature. And that's the way heat flows. Heat is a flowing of energy from one object to a net to the other via contact. In this case, it's actually by uh, dang it, it wasn't convection, it was conduction. Excuse me, completely lost the word conduction. Okay, so that will come in handy later when we learn the first law of thermodynamics. But that's what thermal equilibrium is, and the zeroth law of thermodynamics is, and we're pushing the envelope in terms of time. So let me now show you another phenomena that we did predict, in fact, from the atomic theory of matter, and that's called linear expansion. So there's a linear expansion. And by linear in this case, I just mean something that might be kind of small in cross section, like a 2 by 4. You know, 2 by 4 is like 2 inches by 4 inches. Technically, it's only 1 and 3/4 inches by 3.5 inches. Okay, so that's really substantial size, but when you compare 1.5 or 1 and 3/4 or 3.5 inches to, let's say, 96 inches, it seems really small. So when you have a linear expansion, what we're talking about is one long dimension is expanding. The other ones aren't necessarily that big of a deal. So later that will be compared to like instead of a linear expansion, it could be an areal expansion where you're talking about a whole area expanding, or a volumetric expansion, in which case you're talking about a whole volume expanding. So linear expansion, uh, you probably can figure out that we expect the change in length, delta L, which by the way, remember delta always means final minus initial. So that's L final minus L initial. Just to use the words initial and final. That's why I put the I and the F there. It sometimes you use O and stuff like that, but the change in the length of an object should be directly proportional to the initial length, which again I call it Li over here, but in the equation we're going to call it L0, and it's also going to be proportional to the change in temperature. Again, the change in temperature is going to be T final minus T initial. Okay. But again, we're probably going to use the I's and the O's. So now I can make this proportionality. That's what this is. We could make that into an equation. Whoa, Nelly. It becomes an equation by adding a constant. And in this case, you could actually say, wait a second, it should also depend on some property of the material. So I'm going to put another variable in there. That variable happens to look a lot like the proportional symbol. It turns out to be the alpha. Okay. Uh, and then you could put another constant to make it an equality. What we've done in physics, though, is we went ahead and assumed that's just all one big constant. So what we end up getting is that delta L is equal to the coefficient of linear expansion, alpha, times L0 times T minus T naught. So that's the way we would normally put it, or in more succinct writing, we'd say delta L is equal to alpha L0 times, let's do it times delta T. So this is an equation you're going to use. And in fact, there's another version of it because you can actually break this down as L minus L0 is equal to alpha times L0 times T minus T0. And I'm doing this so you'll see what the deltas actually mean and what the symbols they use. But now I'm going to throw it all together and get you a different form that we often use as well. And that is by adding an L0 to both sides. Then we get L is equal to L0 plus alpha L0 times T minus T0. Or finally, we can say that I'm going to write it back in blue now, L is equal to L0 times 1 plus alpha delta T. So that's another form you can use. And you'll notice right there in section 17, 4, there's actually a table of coefficients of linear expansion. So the table of coefficients of linear expansion give you stuff like alpha for aluminum is 25 times 10 to the negative 6 reciprocal Celsius degrees. And brass is equal to 19 times 10 to the negative 6 reciprocal Celsius degrees. But most interesting is that iron and steel has an alpha equal to 12 times 10 to the negative 6 Celsius degrees. And then L for concrete has a coefficient of linear expansion that's also 12 times 10 to the negative 6 reciprocal Celsius degrees. In case you haven't experienced engineering yet, you wouldn't necessarily know, but that's why we can make reinforced concrete because we can take and, for instance, put steel rebar in suspension so you can actually stretch them, say, and then build box forms around it, fill that up with concrete, and let it dry, and then you have pre-stressed steel. And since they expand and contract at the same rate, it'll take decades before that expansion and contraction causes the steel to break loose from the concrete and making it less strong. So that's pretty neat. There is another formula I'll give you, and then I'm going to let you go. The other formula is basically delta V is equal to beta times V0 delta T, where beta is approximately equal to 3 times alpha. So that's another formula you can use for volumes. Of course, you could imagine a scenario where you do 2 dimensions and do an area, and you get the sort of same result as well. Only you'd expect the alpha to go to 2 alpha instead of 3 alpha. So I haven't given you any examples on that. There's plenty of them on my YouTube channel. I'm calling that as the quote unquote end of chapter 17, but it's really not so much the end. We sort of expect students to have had a little bit of chemistry. So if you haven't, you definitely want to look at those videos. But like I said, I'm probably going to make some more videos and I'll post them. But next time when we meet, and remember, we don't have classes on Monday. I know your class is Tuesday, Thursday, but we don't have classes on Monday. But the next time we meet, you can ask me questions from chapter 17. No problem. I'm just going on into chapter 18. So you guys are free to go. Thank you for coming. I really appreciate it. And I'm going to wait till the last person leaves in case anybody has any questions for me.
Thank you.
You're welcome, Macy. Thanks, Jennifer.
I wanted to let you know the book is open.
Gotcha. I appreciate that. I did check just before class and it was working. So I went ahead and set the due dates and all that stuff. So hopefully that's good to go.
Okay. All
Thanks for
right.
letting me know, Jennifer. I appreciate it.
Yep. Have a great day.
You too. Take care.
Okay, you too.
Bye bye.
Bye.
All right. Well, I guess that's about it for everybody. Thanks for coming, and I will see you next time. Don't forget, everybody, there was a actual additional coverage of material at the end of last meeting. It's at the end of the previous video that I posted on my YouTube channel, so check that out. I think I also typed the section number as N02B for the 242 class and last time, and that was a mistake. It was supposed to be 005B or O05B. I'm going to try to fix that in the actual YouTube video. So just keep an eye out for that. That'll change. But have a good day. Thank you, everybody.